Hello, everyone. Welcome to the book club for Rust in Action. Today we'll be reviewing the chapters 5 and 6, which cover uh, data in depth and memory. Um, yeah, so I guess to start off, I guess in chapter 5, like they cover it goes into like quite a bit into like manipulating bits and ends up at the very final part of it you end up implementing like a smart virtualization of the chip 8 CPU architecture, which I thought was really a great neat way to learn about how to do these things in Rust and like the memory safety guarantees that it provides along the way. um it had been like, at least like for me, it's been a long time since I've ever done anything like this. Like it's not very common that I have to do this in my day to day. So it was nice to go back and refresh my memory on it. Um, it's cool. I saw a lot of themes like the floating points came back. I feel like there's the introduction of floating points early was kind of like leading up to these like things like it's not just something that the author included. It was kind of like this preparing you for how you're going to be actually interacting with it and seeing how they work in depth. So I thought that was like something that was really well thought of as far as like the chapter goes. Um, yeah, I don't know. I'd like to hear I guess like your thoughts on like what you thought of this approach and if there's anything like that particularly stood out to you.
I think you mentioned it further along that the use of implementing the CPU thing was kind of cool. I think I've done like two books now that implements it from scratch, various ways, but it's cool that and it shows how low level you can get very easily and kind of operate at the mid level, like the abstractions are, you can go very high level with like traits and typing and very easily go to the much more what is it called, the operating system level, I guess. So it just kind of shows me the versatility of this particular chapter reinforces the versatility of the language for me.
Yeah, there's like this really interesting point, and I'm trying to remember. I think it was in section 5.1. But so like I think in order to like change a value, like you can't. What I thought was interesting is like if you want to get the binary representation of like unsigned integer, you can do that safely. There's like you don't really need to call unsafe Rust, but for some reason, if you want to get the binary representation of like a float 32, you have to use transmute, which is unsafe. I looked into you can also I looked found this interesting because I looked into the documentation for like F32 type, and they have a method. I think it's called like 2 bits, but the method itself is considered safe. And I think when I looked at it, it says it's like a wrapper around unsafe. Or sorry, it's a I think yeah, it's currently identical to transmute. So I thought that was very, I don't know, like that was probably the first time that something caught my eye. I was like, this is a little strange because Rust is usually very like the language so far I've seen is like very explicit. Like if you're doing something where we can't provide a memory safety guarantees, we'll make it like explicit with unsafe. But for some reason here, this is like an exception. It seems like in the compiler, or I don't know. I don't know if you noticed that, but it definitely stuck out to me.
Unsafe feels like such a judgmental keyword in this language. It's so like, call it, yeah. It's funny when they call it unsafe. It's like, here's this block. Don't, it's bad.
Yeah, it's it's so interesting to me. Like I think yeah, it's a big. I feel like it's a big trade-off the language is made. It's like we will give you these I guess the options to do these things that are like probably not like the best practice in most scenarios, but we're gonna push you to annotate them and make it like, and then now I guess every other consumer who uses your either your code later on also has to annotate it. It's kind of like not cheating. It's like it's just not like not a compiler, I guess, but it's like a way to push um to make it like take a difficult problem of having like trying to detect these automatically and just pushing them to like the easiest solution, which is just have you annotate them. I feel like it's kind of like a in a way like a boring solution, but it's effective.
Yeah, it's interesting. Like you can have like really smart compilers. You can have really like low level things like in C where you do everything. You can have like Ruby where everything's done for you. You don't ever have to worry about garbage collection. And this is such an interesting like in between, right? Where because even with the smart types, it's still like if you have to be you are concerned about ownership, right? You're not like it's not like it's just handled for you, even though it's a very like versatile, like very deep abstraction, you still have to think about it. So it's like an interesting thing where like the compiler is strong, it's very powerful. It also gives you low level guarantees, but also it involves you in it too. So it's it's like unique, I think, from my experience for languages of this type.
Um, yeah, the other thing I noticed in this section was I guess like I added the quote from the book. It's like this is like the developing the strategies for preventing interflow is like one of the ways that system programmers are distinguished from others. And I guess this is like referring to the origins of Rust, which is like a systems programming language. They can do quite a lot, but I think that was like the base use case for it. Um, I guess and like I guess like this prompted me to add the question. It's like I know there's like differences in um there's like differences in like the like I guess like integer overflow protections and like underflow. So uh I think when you're doing just a regular build without any release optimization, it'll silently or like it'll just silently wrap around the overflow. But then if you do the release optimizations, it'll just panic in production, which I think is the correct way to do it because there's way worse things that can happen. Like you can be accessing something you shouldn't be doing, like you can overwrite memory and things like that. But I think ideally you would want to try to catch these earlier. So I'm wondering if it's like I guess I'm like still curious on like what would be like if you were to have like what kind of approach is recommended? Do you have like a test case like every time you're using like this kind of like a specific size or type? Um and then like after that you compile with a release profile and like with cargo also so that you can panic instead of having like a memory like either like going out like not getting the value you expect, right? Or in like C you would get like undefined behavior and then I guess just monitor. um yeah, I guess that was like one of the questions I had. And I think later on in the book they do mention I added this here. They do have like some nice methods that you can use to like if this is like a big concern for you, you can have like the overflowing add method which is provided for you as well. Like it'll tell you if it overflowed or not. So you can check if this was instead of just like panicking, you can probably gracefully handle this in another manner. Um, yeah, I guess that was another thing that came to mind.
Yeah, these are just very specific use cases. Like I think it generically, obviously the book has to be generic, it talks about it, but like it's just not the same use cases. Like Dimitri was talking about rip grep. I was asking for, good examples of or popular Rust libraries. If you look at rip grep, it absolutely obvious well for obvious reasons, but I was actually looking for the chapter 6, the memory stuff. it doesn't do a lot of the like advanced stuff. It kind of looks like a very basic implementation. So I think that that's also part of the language, allows you to do a lot of things easily. But yeah, like it's very specific use cases. Like this is the thing that comes out as a very specific use cases are covered here. I remember looking at a library as for like a personal project dealing with like Bluetooth. It was like a C library, and the amount of macros, like the amount of overhead that that C library does to handle typing, like on this type of Linux, with this type of dynamically loaded dependency, is just like, it's like there's the source code and then there's like 50% of it is macros just trying to handle like sizing of integers. So like it totally is, like I've seen it in like, you know, other projects, how this is a huge problem. It's just like, that's how I reconcile it. Like I think something like ripgrep is like more of a system tool or a command line tool, and then you have the more lower level things that are really like, I can see how this using this system would be make it a lot smaller and a lot easier to read and maintain in the case of like something like that Bluetooth library.
Yeah, I think the other day I saw like in C there's like um I know like integer promotions and stuff like that is like or like it's like a big thing like you have to be aware of, but I think like there's like 257 different like types of like ways you can kind of have this error, which is that's a lot. Like I don't know, to me that's apparently some people can keep that in their head, but I couldn't be able to do that all the time. It's like very hard to do. So it's like, yeah, this is so much nicer to just like have this done for you instead of having to rely on these rules that people have created over time.
Yeah, and even if you have like libraries, I know like for example Qt, the C plus plus as well, but they have a whole thing like where they abstract the integer handling and like various types for you, but it's like you can't really bring it with you. It's not like you're going to take their Qt internal handling and you're going to bring it into another project. Like I mean, probably you can, but you know, if you're the only maintainer, if you're the only author, but chances are you would have some pushback. So it's like um you know that the I think it does show its roots, right? That from the get-go they have that in mind, that that kind of level of like, this is a huge problem for if you're from C roots, this is just a constant issue. So yeah, like I can see the roots of the language in that. The casting, I think it's more prominent in chapter 6, but the casting uh, syntax is really hard. Like it's kind of hard to get used to because it goes like something as something else, and it's like it's hard for me to even parse because there's no brackets. It's just like two words as this, and then you can actually do that. Plus, you can do as well. I guess it makes sense, but you can go as this thing and then a pointer to the thing that it is as. So it's like it's not mentioned as much here because I think these are basic types, but you could also see, like, just following up on that thought, like you can see as much care is taken for casting, because casting, as you said, you can accidentally promote certain data types to other data types and read things you can't or you're not supposed to, or cause overflows. So like that casting system is really interesting. I think that's a good one to maybe look at probably next time. But yeah, just even the syntax is interesting why they chose that particular one.
Sorry, I'm just writing the notes, but yeah, I guess like so I'm just trying to think of like differences on how you would do this normally. Um like in Ruby, I guess you would have like a method, right? You just like call like to like if you want to convert a number to a string to like string, or I guess like something like there's not really any number types outside of like big numbers that maybe I think you would change it. In Go, I think It's you just use parentheses, right? I think that's how you cast it. Like it is definitely different. Like I don't know. I don't know which one I would prefer. Maybe this is like a functional style because you're cast like you can kind of daisy chain them. You can say like cast it as this and then cast it as something else. Whereas in like if you were to try this in like for example Go, which is like the best reference point I have right now, is like you would just I guess you could promote integers into like a different type or like and down, but you would exempt essentially end up with a lot of closures, which I think can be like kind of hard to read. Maybe I don't know. That's a really good point that you brought up. I hadn't thought about like the syntax of like what drove that.
Well, and it goes back to your kind of your first point, the praise for the book, because I think it's harder to kind of understand it until you see the use cases, right? Because like I'm trying to find it so I can paste it and I'll write it out. But there's one in chapter 6, just randomly I found listing 6.5. I'll try to write it as no, sorry. It's like after listing 6.5, but it's like something like let pointer equal 42 and then cast it as reference const to a vec of strings. So if you actually like try to like parse what it's doing, it's like taking the, you know, if you imagine the block, and first of all, you don't actually know the U size, you don't know you don't necessarily know how many bits that is, and then you're actually pointing to something that is a vector, like you essentially created a string in the most roundabout way possible, but it really helps you, or it's a good way to visualize what really happened there, like and how it did it, and also it's part of the unsafe thing. So not a recommend. I'll find it and I'll just type it out actually. Google it.
Yeah, I think it was I think I remember. Is it the portion where they like introduce like the C char and the C string and
Yeah. That was funny. I also that yeah, that one I think that gets it a little bit into like the maze in the language, because they're like there's like convert const u8 to a const i8, which is alias to cchar. It's like yeah, as a I think that there is where they're I think handling a lot of cases that it's very specific, right? It's not something that you know, it's a day-to-day kind of thing. So yeah, I typed that one out. That one is one, and then there's this one, which is I didn't type it out, but maybe that's the one you were talking about, because it's actually pointing at other things. So it'll be like a whole piece of code, but it's like as const u8 as const cchar. Right. So first of all, I find it hard to figure out which way I should read it. Do I read it forwards or backwards? Right. But because I'm trying to figure out, okay, so if I what does it look like after the first const cast to u8, and then cast and then point, right? That's my pointer, and then go again after the second one. So it's like, yeah, I wish if I could wish for one thing, it would be parentheses around the as, but I guess maybe that's a method call, so they want that to be they want it to be a keyword instead.
yeah. Yeah, it is this to me it was very confusing at first. Like if you were to add even one more point of indirection, I feel like it would take me like a good 5-10 minutes just to try to parse what what's the final like thing. And it's also interesting how like you can't you're forced to go like through this chain of casting. You can't directly go from I think that was one of the things they mentioned. You can't go directly from the const you sorry, I forget what the C pointer or the original reference for C is, but um yeah, you can't go directly from the C reference to const C char. It's force it doesn't convert. I think you have to go through this specific chain. Um
Yeah, and that's why that keyword is so fascinating to me, because like the as is does a lot of things. Like it's also like, as far as I can tell, it also has certain guarantees about the safety of that operation. Um, because I think I haven't tried it, but I think I saw somewhere that if you try a certain cast, it might actually the compiler would complain, which is interesting to me that it would know about that. So it's a very fascinating keyword for me. Like that, I'm like I need to. Yeah, I found
It's
it very.
it's sort of like the ML style languages, like in Haskell or in Elm, like that they have spaces delimiting. So basically with the querying and function calls, they're just spaces. And so you kind of have to have the order, the precedence in your head and to know like reading it backwards, like you said, but it just takes some time to get your brain to work that way to parse the spaces instead of if you're used to coming from a C style language or something that's got straight delimiters around there, or that they call delimiters around everything. So my one contribution, I haven't read any of the stuff. I'm sorry, I've been lazy / busy.
Yeah, but that's a good point. Like if we were to translate this cast this into C, like I wonder what that would look like. I bet you it would be a pretty big if you take away the safeguards, right? Like that whole discussion again, you bring it up later, Oscar, about usize, but like there's like a whole set of macros you can get from the standard library just to check usize. If you take that out and you just look at how that cast would look, like I wonder what that code would be like, because I think that again that as hides some abstractions there. So yeah, it's nice. Like it's a bit magical, but it's nice to get that. Just go this, and you kind of have some guarantees. It's pretty cool.
And it's interesting you mentioned the ML family of languages chat, because I think earlier in the book they did mention that this was like a very heavy um like a source when creating a language. So like I think this is like you can still see the roots of where it came from here. It's kind of like
Yeah, the let with the
error.
space, space is basically an operator and in ways that determines the precedence.
Yeah, that's actually like one thing I noted as looking at actual open source projects on GitHub is that it's not as much seen in this book, but I guess it's a design pattern or like a stylistic thing that happens is like there's a lot of functional it's done very like you go something like do the operation and then unwrap and then do something else, but like a lot of the more complicated things like the types as they come back out, they give you more operations you can do. So as you see like the code, it's like the first call and then just you basically go map this like it looks pretty functional in that sense. So it's it's got some of that inspiration, I think.
So I'm a little bit like we talked about last time. I've been proceeding what I've been working on instead of reading. So basically implementing a subset of the REST result type, but in Ruby for the remote development domain library. And it works out really nice. I'm using the same paradigm like with OK and error and then all that included. It took this sort of hierarchical, hard to parse, that we tried to do the best we could domain code and turned it into just a chain of and then, right? So it's these cohesive steps that you pass, the result mode and along. Like and the rest of the team is really happy, how it's going to make the code more maintainable, more cohesive, all of the error handling, logging stuff to now be just at the top of the chain. So it's cool to take inspiration from these functional patterns and especially how REST is, try to apply it in Ruby code base too. And like you can fake a function pointer by just saying, like if you make something a class method or a singleton method itself dot whatever, you can just say class dot method and then pass a symbol to the method, and then that's basically a method reference that you can pass around to a higher order, and then a monad type thing. So it's cool.
So with the RBS, right, in Ruby 3, the type hinting annotation system. I wonder if you could get a lot more. I know it's not probably not part of our standard, but you probably could get a lot of that accomplished, because the nice thing about result is it wraps types, right? And so the types themselves can expose like that's why you can kind of do this unwrap thing, and you can just keep calling multiple as many times as you need really in the operation. You can keep calling the subsequent calls, method calls. So it's like that's something that I guess having the RBS, like the annotation, helps you kind of get that accomplished maybe.
Yeah, mine's really simple. It's like it can wrap whatever you want. Like the key part of it is just being able to have that monadic thing where you can chain these things together, but they're called, asynchronously rather than having to be immediately invoked.
I wanted to add something since you mentioned the result. I guess like how like that's kind of like the, I guess, cornerstone of like the, I guess like the pattern. Um, I think it's really interesting how I have to look up this again and like, but I think it's like early on in chapter 6 they mentioned how results is kind of or sorry, it's well not results option, but I think it's very similar. Um, but yeah, so like it occupies, so option like T, like it occupies 0 space in the binary. It's um because it's the none variant of it is kind of is like basically is a null pointer. But since you don't have that concept of null, it's this is abstracted away from you. In a way, it's like forcing you to check for null pointers without you really knowing you're checking for null pointers. But it also saves the space in the binary. I thought it was like a really neat way how they tackled it, because you don't have to have like, I guess, something separate for none. You just have some, like that's the only thing that you're going to be like referencing to once you have a result. Um, I don't know if that
Yeah,
makes, maybe I did a bad job of explaining that.
it does make sense. Like the exhaustive type checking, and like you can with Ruby 3, you can kind of fake that a little bit. Like there's the case in that you can type check, and you can even check against a structure. But like the fall through, you just have to throw an exception. It's not exhaustive.
Yeah, and the exception handling in general, I think, I mean, not everybody, but a lot of people who maybe come from the more functional side is like they consider it an anti-pattern in a way, right? Because it's just a way to escape the normal flow of execution, and basically it's like a way to branch, but which is like if you look at like how Java or early on one or the complaints that I've heard about Java is from non-Java people is that like basically any method can throw, and if you do not catch it, you are like you need to basically have some catch in the very top, and the fact that you're like I think it's better now, but the fact that you can constantly escape a frame, or that people were using exceptions to escape frames or just actually do other logic, is really a big performance problem, especially in like systems that are lower level. If you start using it as like, I have a parsing error, but it doesn't stop the program. Instead, I just follow another branch or something like that.
Yeah,
And so I think the
using
like
exceptions
capture,
as control flow is that pattern.
yeah,
But which
and
is the
if
main reason we're rewriting like before we start going up the main code with more and more logic. We're like, yeah, we don't want to have exception as our handling, but there's all of these different error cases that we're going to add to the domain, and this, the result in that is a much better functional pattern to reason about that than trying to have an exception hierarchy that you sort out, and it's much harder to reason about that way. Keep the code cohesive.
Yeah, that's a good point about the exception hierarchy, because sorry, I think you're fading a bit. I wasn't sure if,
sorry, yeah, these earbuds are great.
No, I was just gonna say, like, in certain, like Java, probably other languages too, like the exception hierarchy can end up looking like very much like its own code, like like a side by side class system with that, and the exceptions do their own thing. Like there's an actual like logical flow to them. The reason I was reminded is because of what you guys just said, which is like, you know, the having this result type is just a way to like basically, you know, take that out, take the need for like for exceptions as like basic levels of like a control flow, and like bring it back into the program, much like Go does, right? But Go treats it separately via like, you know, via a convention, right? And this is a convention too in a way, but I think it makes it a lot easier than even Go's. It's why I really like learning this, because it really looks like an evolution on, and you could see sort of the inspirations it takes from different places.
Yeah, and you can like you can still be idiomatic within use these patterns, but be idiomatic within the language that you're in. For example, in Ruby, like if it's a like for example the pattern matching, or if it's like this is a bug, you know, this is definitely our problem, a coding error, it's going to be a 500. That's fine. Throw an exception and let it bubble out the top. But if it's like a domain, you know, this is domain handling code, you know, branching logic that's related to our domain, that should be an exception. Try to handle that instead. The result in that then chain.
Yeah,
Yeah.
and actually remind. Sorry, go ahead.
Oh, sorry. I was just gonna add like I'm so like I'm working on an MR where um there's a possibility of like something like you're not like not enough of the like where we don't control this, like the user input doesn't provide enough information to do something like specifically. And the at least like, so I'm not as well versed in Ruby as I am in Go, so at least for my knowledge, just like I think it's like in this case you would have to like throw an exception like to make it known, like I guess track it somehow. And that made me like, it made, I don't know, I like after going through the book I'm like, oh, I really wish I had this option just to like take like the none variant and not, you know, like not have to throw it all, like let it bubble up and hope some like I catch it somewhere else, or like someone else later on catches it.
Yeah. So most all of the stuff I'm doing is completely isolated in our remote development domain. So people shouldn't care too much what we do there. Um, but I am gonna try to put the result class that I wrote at the very top level, like in lib. So I may, if I get pushback on that, I may call y'all in to try to get your opinion on it. It would be nice to have this discussion in the Ruby code. Well, I hope I don't get pushback. I think it's a nice pattern to have. I have this fear of like, you know, where's the line where I'm pushing it? Because obviously you don't want to try to do curry. Even though you could, that would just be incomprehensible and, you know, and make the code unreadable. Whereas this and then pattern, there's tangible benefits. You're keeping your business logic cohesive, you're decoupling your error handling, and you have to organize your code in a much more readable, linear way. Uh, but like trying to find that line, how, you know, don't go overboard with these structural patterns where they confuse people and go past Ruby idioms, but still use some of them to give you the benefits you want. And I struggle with finding that line, you know, making the code base still understandable where everybody can contribute.
Oh, this is I'm excited. This that would be so helpful to have, at least as someone who's like newer to Ruby. Um, this is, yeah, I think that would be amazing to be able to use.
Yeah, and the larger efforts to like for the modular monolith, I think it can only help to just be more explicit about, you know, where the boundaries between your domain code and the rest of the app, and using patterns to make that more explicit and types whatever you can. Yeah, I didn't read
Um,
this, but we're getting into the like implementing a compiler. This is the thing, just that, like you said, the range of what you can do with this. Like this is really low level stuff. Higher abstraction stuff with it as well. It seems like it's really a flexible language.
yeah, it's kind of cool. Like also like I put it on like I think one of the points below, but they also even left like um I think like there was a challenge there. They're like, if we can make a way to like uh I think it was like create like a random number between 0 and 1. I think was the like using like the floating point representation. And they're like they left the challenge like if this is how I could do it, but if you know a better way, you know, feel free to try to improve on this. It's kind of cool like um the flexibility of options it gives you. It's like this is the guided portion if you want to go even further and like see how to optimize it like in a performance or focused manner. You can do that yourself. I don't know if anyone attempted this. I did it. I'm not that well versed, but it was cool to see that that's an option as well.
But and this was like a really good example of like low level versus high level Rust and what you can do like freely without too much overhead is like you know, it lets you do these operations and kind of move within inside of a type if you think about it and accomplish like I mean this is a kind of a trivial thing though it's pretty cool I never even thought of doing it this way but it you know you can fairly easily accomplish something as low level as this and as you know as high level as some of the other examples we've seen so it's pretty cool but yeah like that was a great exercise.
Yeah, I had some I guess like some other like small thoughts I wrote down. Well the last one I had was um and feel free to stop me. I don't want to take up all the time, but I thought it was interesting. Like there's like one little I guess like small detail on like how um there's like a lot of implicit like memory guarantees here. So like usize is cool for like indexing. Like it enforces this as the only way you can index like a slicer like an array. Or sorry, I think it's yeah. So I think a slicer array, but it's because that way like if you're happens to be let's say like on a 60 or 32-bit system, you can't use a 64 uh we can't use an N64 to index because this would be like out of bounds. So it forces you to use the one that's like for the machine at the time instead of potentially like doing something like dangerous like this. Um yeah, it was really nice. Yeah, those were the ones that I had at least for chapter 5. I don't know if anyone had anything else there. I can also discuss like 6, which I think is also really interesting, like the focus on like the different pointers that you have, like the different references and tools you have available.
Yeah, just a point you said, I was just trying to look up a library that demonstrates like a C library that demonstrates the problem with U size. But yeah, like I said, I can't really find it right now, but sorry. Uh, and I think the more modern, I was looking at the kernel. Kernel does a lot better job at everything. Like it's all implicit because of the stuff it includes, but you know it's there if you look at the qt if a qt code it's got you basically have to go like use you know qt colon allocate me some you know and don't tell me what size unless you want a specific size right um or like older c code will whatever it's still in use like probably in grep and various tools but older c code will actually just use macros and ask for you know I just want an int that I can use and then you know you assume the frame for it so and the thing and that's how you can I guess catch overflow right because if you compile in a particular system you can catch it at that moment though if you know get a binary you know get a binary of a different from a different system you can run into a bad result so the fact that that's like what is it called? Like, I mean, other languages have it. Like in Ruby, you can get an int, right? But but the but the nice thing about this is that you can get sizes that you want, and it's like a basic unboxed primitive. It's not like anything special that another language would wrap for you in order to give you all these guarantees. So like it's not that special. Like it's not a crazy feature, but it's a really useful one, I think, for low level stuff from some of the libraries that I've seen.
Uh, yeah, I saw the so like on the observation you added as far as like the unit testing, like I guess like the how there's like seems to be sparse on the Rust projects. But that was
Yeah.
an interesting uh, observation, because I wonder if this is related to like the way the compiler, maybe there's more trust in the compiler doing things for you, so you're mostly focused on business logic and not on the like just catching all these things like yeah, like I know for example in like for like dependency scanning, I think we use like pointers in some places, like so you have to make sure you're like, oh, I'm not going to be using like I'm not dereferencing a no pointer like later on, and this causes like a stack trace in the middle of the program like panics.
That's a great point, and it goes back to what you and Chad were talking about with like Ruby, right? To me, maybe this is an unpopular observation. I think I've had arguments about this before, but to me, what a large part of Ruby unit test, especially like say in our Rails thing, it's actually type checking. It's actually like you look at it and it's like, does this thing return what we want? But it's not like does it return with this value? It's literally like, does this return, you know, it's the one that I dealt with recently. Does it return a hash or an array, or does it return this class? Let me assert the type of this class. Like, is it returning the right kind of class? Because it might, this service calls this other service. I need to be sure which one of those. But it's like, to me, that's like, and you can see it in Go as well, right? Like a statically typed language, you see half as many, well, half, you see like 90% less tests. And to me, it's not because they test less, it's because they're actually testing business logic and they're not testing composability. Yeah. So like, I don't know if you can make a jump to Rust saying they're even strongerly typed, but what I like to look at is in every chapter, I would look at an open source project just to compare how they do something. And like, I've looked at a bunch of them so far, and it's like most of the tests that I've seen are all integration tests. Like they test the binary at the call level, calling the whole thing. I haven't seen too many ones that actually, test underneath the unit of work. So that's just my observation. I haven't looked at it too deeply though.
Yeah, that's something I noticed too. You should be able to hear me further. I didn't realize it was from that code. But when I first started using type, started with Kotlin, I realized that huge difference in what you had to test. And I think of it in terms of the testing pyramid. Have y'all heard of that? Like the testing pyramid is like at the bottom of the pyramid is your unit test, things that are at functional, like the individual method or functional level. You have a lot of those there. They don't fail. And at the top is your actual user, where you're directly manipulating the browser, CLI, integration. And but the middle layer is like, multiple components working together and stuff. But it's also like is everything glued together in the right area, the right type, and in a a strongly type inferred language, you have almost no tests there. You don't need that because the compiler won't even compile if you do it in a weakly typed, non, null having language such as vanilla JavaScript or Ruby. Like you need a lot of tests in there just to say, is everything glued together? But with some of the stuff I'm working on now, like there's some features coming even without RBS or sorbet, which are, sort of bolt-on type systems for Ruby built into the language itself in Ruby 3.0. You can do some type check. Like with pattern matching, you can say, hey, when I destructure this, it's got to be this type, and it will throw an error. It's just not that type when you destructure it, or when you in your case statement say this has to be a hash when this type is this key. So you get a little bit of that coming in. I'm hoping to start using that in those new areas, greenfield areas. Because yeah, when you start, when you like, I worked in Ruby and then I switched like maybe 6 months or so, and I came back and oh my god, yes, null pointer, and the find is not a function. I have to write tests to catch all of my stupid things that I relied on the compiler to catch for me in the other language.
Yeah, because a lot of the memory safety guarantees or type safety guarantees that a dynamic language brings you, they kind of avoid like the whole class of C errors where you rely on something, but then it's pointing to an invalid space, right? Fine. But then the way they solve it is like, well, you either instantiate the object or you don't. So you either get it or you get a nil. So it's like, I mean, I know it solves it in that you still get a nil and you're stopped at well, it is runtime, so it's not the best, but you're not accessing invalid memory, but the behavior, if you just look at the behavior of the program, you still got an expected result. You didn't get something that you expected X and you get a nil. I mean, I know, yeah. And the same thing with Go, right? Like in certain cases, if you want, I'm trying to think of the example, but if you want a if let's say you have a constructor or some kind of factory thing that gives you an object back, but in certain cases you just want to return an error, right? Like you don't want that I don't want to build it. I just want to give you the error because I couldn't construct it. Unless if let's say you have the return value has two values in the return, one is the object, one's the error. If I don't return a pointer, I still have to instantiate that object. Probably it's not that expensive, but it could be under certain circumstances. It could be expensive, right? So what does that mean? That means that you can still return a nil, right? Because it's a pointer. Like I have to give you a nil in order. Like if I don't want to go through the whole thing of creating this object, right? It's too expensive. There's like, let's say some attribute that I actually have to calculate. I have to calculate a sub object, something like that, or substruct. But if I don't want to do that, because I can't give you just the empty object, you have to get that pointer. And the negative part of it is that like further down somewhere else, I can't rely on the fact that I'm just going to get an error. What if I did get a nil for some other reason, right? For another reason, out of sight of the logic of that construction. So even with Go, you have that potential to get like this. It's I guess it's more of a pattern, or more of a, I guess what is it called, like a just like more of a convention, less than what the language forces you. So it's not as bad as some other languages. But yeah, it's nice to see Rust not do that, and just yeah, it's nice to have a result. It's good. I like that a lot better.
So I think sorry, I know, I think we're out of time. I don't mean to keep anyone past. Just wanted to add one last thing as far as like, at least I like, as far as chapter 6, I thought it was like, something that I personally, I feel like I still need some practice on. There's so many different, like they make a lot of notion, or like they put a lot of focus on the notion of like references, pointers, and raw pointers. It's kind of like I guess like an escalating function as far as like how unsafe you are. Like it continuously gets a little bit more risky. You have to pay more attention when you're using them. And then there's just so many different ways, like I guess like also like it forces you to think about like versus the stack and the heap, because of like how you're wrapping types. Like if you take like, for example, like a string, like the static string, the one that's like yeah, like a static string, like you can potentially move it to like use it using like a cell, or sorry, like a box and things like that. I feel like this is the part where I'm at least I'm having some trouble. It's gonna take me some time to like I guess, get over this learning curve is like there's just so many different ways you can use it. Just like cells, ref cells, copy on writes. And I think like later on, if you want to do something more advanced, they have like the unique and the shared pointers that you kind of can build off yourself. And yeah, that's just more of a thought, not much of yeah.
Yeah, for sure. I mean, it just as a like if you look at again, because it like I like to look at the open source projects just to see how it's used. There's not a lot of usage of these really smart pointers, like all these like fascinating ones. You know, that card system that they created, the trading cards. Further down the trading cards, down and to the right, there's not that many of those used. And
It's
one
like the
last.
periodic table, those ones at the bottom right. Never
Yeah, I think those
existed
are
in the
very
real world.
specialized. Yeah. But there's listing 613 is the one that like kind of blew my mind, but it was like also not disappointing, but a bit scary. So line 6, I'll just type it out if you guys don't have the book, but it's like, so I thought that unsafe block, you just do an unsafe operation and you're out of it and you're safe, right? Which probably is naive, right? But if you look at what I'm typing, this is the code. So you could do that, right? So you can assign, you could do something unsafe. I mean, obviously you could do that, right? But it's directly like having this idiom implies to me that that is possible, like a lot more possible than what it implies. Like unsafe block, let's do an operation. Maybe it'll fail, maybe it won't, but we're out of it. But now we're just like, we're allowed to assign that way. That seems a bit like, you know, it's easy to. I mean, obviously it's nice to have that statement and have that piece of code. Is just the fact that you're able to assign the result of a block doing that. It seems like, you know, there's a way it's breaking a bit that boundary, that safety boundary that it kind of gives you from the beginning or advertises in the beginning.
Is that bubbled up like as an attribute of the cargo crate? Like you can specify, you know, I'm gonna get warned or I can fail if any of my dependencies do have any kind of safety in them.
Yeah, that's a great point. I wonder if there are any annotations on cargo that allow you that warn about unsafe usage. I'm not sure that that's but either way, like especially if you're building a library, I guess if you were building a library, yeah, that would be useful because then whatever code, oh yeah, who knows if that would be useful. If it was source, it would warn you, but if you were building in yeah, I guess you would have to have 2 levels of warning. One is a pre-built library that you pulled in, that might be unsafe, versus source that might be unsafe. Or I wonder if you would need that anyways. Like, and for what it's worth, I haven't seen it. Like just looking over things like ripgrep or what's the other one that I looked at? I looked at this thing called TickV, which is it's a key value database. I haven't seen a lot of like usages of those levels of like unsafety or even more complex smart pointers.
Well, thanks a lot for doing this and indulging me for showing up again without doing the reading. So nice to listen.
Yeah, thank you for joining. Yeah, so I think
I
we're
feel
out
like
of
this would
time.
be an intense book that it would take me a lot of investment of time if I wanted to do it.
Yeah, I have not done all of the code myself. I have I'm gonna be I know James knows the author of the code because they used to work together, I believe. But I was gonna submit some feedback because I think there is some portions where like the code itself, like even if you like the pre-packaged code, if you wanted to run it, it doesn't run automatically. You have to like comment out stuff and um but yeah, I think it's quite a lot of like it's very dense for sure. Like there's so much that goes into it. Even um understanding the floating point thing, it's like you have to really go back and like look into like very specific, I guess, knowledge like the mestizo, like a floating point, and all these other concepts. It's just a lot to take in. Yeah, I thought that was a really cool thing about the checking to see if you have unsafe code in there. I was gonna ask the static analysis team if they, I don't know if this is something like they could catch, if this doesn't exist already. Like, that'd be kind of cool to say, like, hey, if you run your Rust code, we have this rule that says this is where you're using unsafe, and this is where, you know, if you could probably prioritize as like on an issue list. I mean, I feel like I would find value in that, but I'll add that as a to do, and maybe next session let you know what I found.
And what I'd
Yeah.
really like to see is like real world examples of code using unsafe, like how it would be used unsafe, because between the casting and the really strong type system and then the like low level things you're allowed to do, like I'm curious about where unsafe fits in that ecosystem. Like where is it real world used?
If you're like any in TypeScript, it's just like the lazy person's way out.
Well, thank you so much for joining. Yeah, I'll be uploading this recording shortly after, and wish you all have a great rest of the day.